Kia ora and welcome to the first screencast for 297-101 Statistical Data Science, where we're looking at Workshop 1. So I'm going to start by going to week 1 on stream and going down to the workshop and clicking on it, and we get our workshop guide. And then we just read through the workshop and you can see that there's some work to do if you haven't already installed R and RStudio. I assume you have already. And then we're asked to load up our first R script. So it says start by downloading lab01.r to somewhere on your computer. The easiest way to do this is to right click on the URL and save file as. So in my browser it's save link as, but that's somewhat similar. And I'm going to choose a place to put that. So I'm going to put it in my 297-101 folder. I'm going to make a new folder there for screencasts. And I'm going to put it in there. Okay, so that's saved that file onto our computer, and now I'm going to go into RStudio, which is this here. Okay, so I've just loaded RStudio up, and then I'm going to go to File, Open, File, and I'm going to browse to that location, which I'm already in, and go to Screencasts, and there's the file there. Okay, and there it is. So before we get cracking on things, a quick overview of RStudio. So RStudio is an integrated development environment for interacting with the programming language R as well as other programming languages such as Python and various other things. And so the actual computer coding software is R, but we don't actually interact with R by running R directly, right? So we interact with R by using RStudio, and that then runs the R code for us. So down in this bottom left-hand corner here, we have our console. This is what R looks like. So R is a console app on most platforms. And interacting with the console app is a bit annoying, so we're going to use RStudio to do so. So you can see that basically things are split into basically 4 panes. I've got this script loaded in this top left-hand view, which is where we will be doing the majority of our work. But there's other views. There's this console down below, which is where all the actual computing gets done. We'll see the editor view interacts with that for us, and so often we don't actually have to type anything down here. We can just do it all in the editor view. We've got some other things though. We've got environment up here, so this is going to be where our data is stored, and the various variables we have loaded will be located, whether they be data sets or various other things. Functions and so on get loaded up here as well. We have our history, which is everything we've typed before, and various other things. And down here we've got a file browser. So this is the current folder that I'm in, or the project that I'm in, which has all the stuff for this course. We've got the labs, the lectures, and so on. And then we have a plots tab, which is currently empty because I haven't done any plots yet. We've got packages. So packages are basically add-ons for RStudio. Okay, and we're going to be using some add-ons for RStudio. Some of you may have, when you open the lab01.r, you may have got a yellow banner across the top that said something like, this R script utilizes the tidyverse package, which is not installed. Would you like to install it? If you do get such message, just hit the install button, right? Let it do the job for you, and it will install it. So the list that we have here in the packages menu are all the packages that I have installed on this computer. And so you can see that I've got a lot. They're not the packages that I have loaded for me to use. They're the packages that are on my computer and available for me to then load and use if I want to. So there's 2 separate concepts. There's the getting the package onto your computer, and then there's the loading the package from your computer so that you can use it in R. Okay, so that second thing, loading the package from your computer so that you can use it in R, is the library command, right? So library tidyverse loads up the tidyverse set of packages so that we can then utilize them. Okay, the reason that's important is that we're going to be using functions in those packages. So for example, down here we've got this ggplot function, right? If I just try and run that line of code now, you can see that I get an error because it can't find the function ggplot. That's because the function ggplot is in the package ggplot2, which is loaded via library tidyverse. Okay. So that's loading something from your local computer into the program, but there's also getting the package onto your computer in the first place. And that's done via a package installation, which you can do via the install button here. So you just click install, type in the name of the package that you want, and away it goes and does all the work for you. Okay. So I'm going to assume that you've got that far, and that when you run the library tidyverse command, you get a bunch of stuff spat out down here. Okay, so you can see that I ran this and it says attaching core tidyverse packages, and it's told me the packages and the various versions that it has. So I'm loading tidyverse 2.0.0. You might have a slightly different version, it probably won't make any difference. And then we've got some conflicts down here, and I'll talk about those in a moment. Now to run that command, what I did is I put my cursor on the line in question, and you either click the run button there, run the current line or selection, or you can see the shortcut there, Control plus Enter, or Command plus Enter on a Mac. So I pressed Control Enter then to run it. Okay, so the script that we have here, the file that we loaded up, has a combination of lines of code like this one, library tidyverse, which is coloured usually in white. Well, it depends on the colours that you use. Obviously I use white on black because it's nicer on the eyes in my view, but I think the default is black on white. You can change that under tools, okay, appearance. But we also have some orange here, which might look, I think it's green by default. And these are comments. So anything preceded by a hash, okay, is interpreted by the software as being a comment. You can write whatever you like, and it will never be interpreted as code. So it'll never try and run that, because of course the narrative that you're writing is not interpretable by the computer directly. Whereas the code lines that we run must be interpretable by the computer directly. Okay. So we've loaded the tidyverse, and it loaded a bunch of packages. So our ggplot function is now available. We can see the ggplot2 package has been loaded, but you can see we also have some conflicts. Now the conflicts, you might have slightly different ones than me, but you'll probably have these ones at least. You may also have one for select, depends on which other packages you have loaded at the time, which depends a bit on the R version. But basically what happens is that there's a function called filter, which we'll be using in about workshop 4, I think, which takes a data set and returns only a subset of the rows in some way. So it's basically for filtering out things you don't want, or for filtering in the things you do want. And you can see that filter function inside the dplyr package is masking the filter function inside the stats package. So the stats package is a package that's included with R, and that also has a filter function. So now we've got two filter functions, one in the stats package and one in the dplyr package. And all it's telling us is that the dplyr filter is now going to be the boss. Right? So when we type filter, we're going to get the dplyr one, not the stats one. So it's just warning us that, hey, you've got a conflict here. You've got two functions that are named the same thing. So one of them is going to take priority over the other. We can still run the other one if we want, but we just have to prefix it like this. So if we wanted to run stats filter, we'd have to type in stats :filter. Okay. Generally, that's not something we have to worry about too much in this course, so I don't think we'll get conflicts. But if it gets to the situation where we're sort of prepared to at least know why something might not work. How to fix it, we could then Google, right? So the next thing we're going to do is we're going to load some Quakes data from Fiji. And you can see that when I ran that line, it didn't appear to do anything. So it copied the code down here and executed it, but we got nothing out, except for this thing up here. So we can see up in our global environment now, I have this Quakes thing that's a promise. And a promise is just basically R is telling us that, hey, it knows about quakes and it'll make it available to you when you have a look at it, when you want to really have a look at it. So it's just sort of a lazy loading thing, if you know about that in computing. So if I click on that, it then tells me, hey, quakes, we have 1,000 observations of 5 variables, and it actually spat it out down here. So we can see what the first bunch of rows are. We can see it's got columns of lat, long, depth, mag, and stations, and a bunch of numbers. Okay. We could double click on it, and it will load up the data for us in a sort of a spreadsheety type view that we could then scroll through. So we can see that we've got 5 columns, lat and long, which is the location, latitude and longitude of the earthquake. We've got its depth, I'm not sure what the units are there. We've got the magnitude, so how big the earthquake was. And we've got the number of stations at which it was felt or detected. Okay. So that's what we've got in our quakes data set, and this is the data set that we're going to be using for the first couple of workshops. And so the next thing we're going to do is do a plot. Okay, so I'm going to run that line. So again, I'm just going to put my cursor anywhere on those 2 lines. The second one is fine, and I'm going to control enter to run it, and now we get a plot. So here's the plot here. So you can see that we have a plot of mag, which is the magnitude column, versus station. So we've got a scatter plot of 2 variables. So each point on the plot represents the combination of mag and stations for that particular observation. Right, so I've got 1,000 dots here because there were 1,000 rows in our quakes data, and for each one the x coordinate is taken from the magnitude column, the mag column, and the y coordinate is taken from the stations column. Okay, so you can see here that there's quite a bit to type. Okay, in our to produce a plot, right? It's not just like plot quakes or something like that, because we have to tell it which data set to plot, and we have to tell it which columns to plot, and we have to tell it what type of plot we want, right? But there's a recipe to it, and the recipe is always the same, just we sort of change the ingredients here and there. Okay, so as we develop more sophisticated plots, we'll be adding more ingredients, but the basic recipe will still be the same. So the recipe is as follows. We always start with ggplot, the ggplot function, which creates a plot. Okay, and the first argument to the ggplot function is which data set do you want to be drawing on in this plot. Okay, so which data set do you want to be pulling information out of? And so we've specified here on this first line that we want a plot of the quakes data. Okay, so breaking this down a bit, the ggplot function is used to start a plot and assign a data set to it. Right, so when I run just that bit without the plus, I just get a blank plot. Okay, so this just gives a blank plot and associates the quakes data with the plot. Okay, so step 1, tell R we want a plot. Step 2, associate the data set we want to plot. So this is ggplot, and this is data equals blah, right? Right, so this is our recipe. Okay. Let's just leave the steps in there. Okay, the next step is to say what type of plot we want. Right, so the geom point bit here, right, is telling us that the ggplot function that we want to do a scatter plot. Right, we want to have a plot that exhibits points. And of course, before we can do that, we've then got to say, okay, we want points. Which points, right? What should I use for the x and y coordinates of those points? Okay. And so those are done using what's called aesthetics. Okay, and it's done by by setting up a mapping from features of the plot to features of the data. So step 4 is define what variables we wish to map to features of the plot via AES. Okay, so we can see that the AES bit here, if I just run that bit there, if I just pull this out, okay, the AES bit sets up an aesthetic mapping. So features of the plot to features of our data, which will be columns or variables in our data set, right? So here we're saying that the x coordinate of points should come from the mag column, and the y coordinate of points should come from the stations column. Right? So altogether we have our plot. Now notice that we've joined those two commands, the ggplot function and the geonPoint function, with a plus. Okay, so the plus connects multiple functions within a single ggplot, single plot. Okay, now it's important that the plus is on the end of the line rather than being on a new line. So a common mistake, so it's important that the plus is on the end of a line, not the start of one. Right, so if I just made a mistake and pressed enter there and put the plus on a new line, then, you know, logically to us humans, these two things are the same, right? In that we're kind of adding the geonPoint bit onto the ggplot bit, and we're kind of doing the same thing here. But according to the computer, they're not, because at the end of this line, it has a complete statement, right? We've got the, we're invoking the ggplot command, we're feeding it a data set, and we're closing that bracket off, and that's it. Right? There's no hint from that line itself that more is coming. Now, us humans are smart enough to look at the next line and see the plus there and go, oh, actually, more stuff is supposed to come. But the parser, in terms of the computer figuring out what to do, is way simpler than us humans, and so it's too dumb to look at the next line. Well, that's not quite true, but as soon as it gets to the end of a line and has completed a full statement in terms of, you know, brackets, and it's not looking for anything after a plus or a comma or something, it knows that it doesn't need to look at the next line, and so it can just run that code. So if I try and run both of these lines at once by selecting them and then hitting run or control enter, then you can see I get an error. And the reason I get an error is that the first thing it did is it ran that ggplot data equals quakes, and I got my blank plot. And then that's like, you know, that's end of that command, and then it ran the next command plus geonPoint, and is like, oh, I can't use plus with a single argument, right? You can't go 1 plus, right, and leave it at that, or plus 1 and leave it at that, because what do I add the 1 to, right? So it gives you an error, and in fact in this case, which isn't often the case, we actually get an informative error. Did you accidentally put plus on a new line? Indeed, that is what we did, right? So what you've got to remember is that you always put the plus after the statement and before the bit you want to add on, okay, on the same line. So you can either put them all on the same line or a little bit tidier, one after another, but keep the plus on the line before. Okay. Now, of course, we can change things in our plot. I'm just going to skip over and make sure that I stick to all the points in the workshop rather than just making up it as I go along. So the first thing we want to do is, of course, describe our plot. Okay, so what do we see from this plot? Well, what I see is it is a plot. So I'm going to put a hash there so that it's a comment, not code. It's a plot of magnitude versus the number of stations that detect the earthquake. There looks to be an increasing trend that is maybe fairly straight, with some scatter about the trend. So what I'm doing there is I'm commenting on what I see in terms of trend. So what is the average number of stations for each magnitude? So I'm kind of imagining a sort of a line or a curve that goes through the data here. And I'm saying that that line or curve is going up, right? So as the magnitude of the earthquake increases, the number of stations at which we detect it increase. So that's an increasing trend. You might say that it's a positive trend, it has a positive slope or something. And then I've sort of described the shape of that trend. So I've said it's reasonably straight. It's mostly straight, isn't it? Maybe there's a bit of a curve at the bottom. And I've also then described the amount of scatter about, or said that there is some scatter about the trend, right? Because that's kind of important as well, because what you want to know is, if the points were tightly clustered around the trend, so there was very little variance in y, in the number of stations for a given magnitude, then the magnitude would be a super good predictor of the number of stations at which you detect it. Instead, we've got quite a bit of spread here. So you can see a magnitude 5 earthquake ranges from about 20 stations up to 100 stations. Right? So there's a large amount of variation in the number of stations at which detect an earthquake for a given magnitude. And that's, of course, because magnitude doesn't explain all of the variation in the number of stations. There's other things about those earthquakes that pick up whether a particular station will detect it or not, right? For example, how far it is away from the station, right? If the earthquake's on the other side of the world, to Fiji, where these stations are, none of the stations would probably pick it up unless it's a really, really big earthquake, right? So there is a relationship with magnitude, right? The bigger the magnitude, the more stations would pick it up. But that's not the end of the story, right? There's other things going on. So while magnitude explains some of the variation in the number of stations to detect things, it doesn't explain it all. So the next thing to talk about is, are there any odd observations, perhaps? So we might think that maybe these ones here are a little bit odd. They're kind of off the trend a little bit, aren't they? So these ones are ones that are bigger earthquakes that have been detected at only a small number of stations. So those are a little bit odd. And we've got another one here that's a smaller earthquake, but it was detected at a lot of stations. So maybe there's something else about that earthquake. So there are a few earthquakes of magnitude, what's that, about 5.3, that were detected at fewer than 20 stations, which is unusual given the trend. Right, so we might want to say something about that. Right, I'd only pick things out that are really clearly odd. I wouldn't necessarily comment on this one because it's kind of fitting the trend. So sure, there's a gap here, right? But that's just because, partly that's because there are fewer earthquakes that are really big, right? Which is a good thing, I suppose. The other thing that we might want to think about is, does what we see on the chart sort of fit in with what we might know already about this situation of earthquakes? So would you expect the number of stations at which an earthquake is detected to increase if it's a bigger earthquake? And of course, I think you probably would, right? If it's a big earthquake, then it's going to be felt more widely. Therefore, the number of places that you'll be able to detect it with a earthquake meter, whatever they are, would increase, right? So we could say this makes sense given the variables we're dealing with. We'd expect larger earthquakes to be detected more widely. Okay, so the idea here is that the statistical evidence that we see from the chart is sort of supporting the other evidence that we already have, right? That comes from the domain of the data, comes from external to the particular data set that we have, right? That information is based on our knowledge of earthquakes, not the data itself. So adding to our plot, right? We can change lots of things about this plot. Essentially everything you see in the plot can be changed, right? We can change the axis labels here. We can change the style of the points. We can change the background color. We can add a title. We can make this white black if we want to, or bright green. Lots and lots of things can be changed. And so what we might want to do, for example, is change the color of the points to pink, and maybe change the size to 3. Okay, so you can see here that we get the same plot, but now the points are all pink and bigger. Okay. Handily, the editor has correctly found and identified the color pink for us and made it pink, which is kind of neat. One thing to note is that the pink is in quotation marks, and that's because pink as an object is not known to R. So if I get rid of the quotation marks and try and run that, I get error object pink not found. Okay, now this is a super common error and is usually because of a typo in some case, right? So for example, let's fix up the pink so that it's not an issue by putting quotes around it. But we'll change these S in stations to a capital and run it again. And now you can see that we get another error. Again, it's very, very similar, right? Object stations not found. Previous one was object pink not found, right? And it's because of the typo, right? So R is case sensitive, so little s stations differs from big S stations. So if you get that error, the most likely explanation is you've made a typo, right? So you've spelt something wrong, or you've used a capital letter when it shouldn't be. So the idea is you go back to the data and just have a look inside it. You can even copy from the data. So you can just go into there and note down the actual name of the variable. So a common trick is to actually just type the name of the data frame into the console, right? And it spits it all out. And then if you just scroll up, you find it, you can actually just copy and paste it, right? Copy, paste, and then we get it right. Okay. So there's other parameters that we can use. So obviously there's different colors. So we have this terrific color green. There's nicer greens as well, green 3. There's obviously size, there's shape. So we can go squares or diamond. Okay, squares on an angle. Is there a star? Yeah, there's a star. Look at that. Okay, various other shapes are available to you. Obviously, you can change the size, so you can shrink them down a bit, make them small, or whatever. Okay. There's also alpha. So alpha makes things partially transparent, depending on the number that you put. So alpha, it takes the number between 0 and 1. So 0 is fully transparent, I think. Let's try. Yep. And 1 is fully opaque. Right, and then values between 0 and 1 are in between, right? They have some transparency to them. To find out what these aesthetics are, we could use the help for GeonPoint. So if I press F1, while my cursor is on GeonPoint, so F1 on your keyboard, then you get the help for GeonPoint. You could also just search in the help, right? So you could just type in GeonPoint in there. So the point geom is used to create scatter plots, and it shows you a bunch of information about what the various arguments are. So it's got the mapping argument, which we already know, and then it's got ... which is everything else. And down under ... we've got aesthetics. And if you keep going down, it tells you about the aesthetics. So these are the ones that it requires, X and Y, but it's also got all these other ones that you can use. And it says, learn more about setting these aesthetics in Vignette ggplot 2 specs. So the idea is, because this isn't a code type, we can copy and paste that code and run that. And there are the aesthetic specifications, and you can see that we've got color and fill. So colors can take a name called like red, right, which we can list them all with colors. Okay, so let's write some stuff here. Find out about all the aesthetics. Aesthetics with Vignette ggplot 2 specs, and then colors. Right, so if I run colors, then it spits out all the different colors. So you can see here we can, we've got this one here. Let's chuck that in and see what that does. Oh, that's a white, so it's probably not that exciting. Let's try moccasin. There we go. It's a lovely sort of beige color. Not ideal with the grey background, perhaps, but there's a huge number of colors that we could try. There's light steel blue too, for example. Steel blue is a favorite. But there's also other things. So there's the line types, lots of things to do with that. These are all the shapes. So those are all the shapes that you can use. Some of these have a fill. So circle filled has an outside color, which in this case is black, and an inside color, which is red. Okay, which differs from circle, which is just solid black. Okay, so there's a fill color and a color. So for example, if we changed it to circle filled, we could specify fill equals purple. And when I run that, you can see that on the outside, you may be able to see that on the outside we've got a light blue. Let's change it to yellow. See if we can see that. There we go. So on the outside you've got yellow, and on the inside you've got a purple color. Let's swap them around maybe. Right, so there's lots and lots of different aesthetics that you can set. Okay, lovely. Now it's important that when we set an aesthetic, you notice that when I set the color, let's maybe go back to a slightly less horrific one. Just get rid of all that. Just stick with purple points. When I said that the color was purple, it changed the color for all of the points. Okay, and that's because we've set the aesthetic to a constant thing. Okay, the alternate is to allow the aesthetic to change based on features of our data. Right, so that would be done by mapping the color aesthetic, so the color of the points, to a column in our data, just like we did for X and for Y, right? So the X coordinate and the Y coordinate are mapped to the mag and stations respectively. We could also map the color to something respectively. And to do that, we would have to put the color command inside the AES. Okay, so to map the color to features of our data, we need to put the cull argument inside the AES. So a common mistake is putting the cull argument inside the AES, but when we're instead trying to set the color to the same, to be the same for all points. Alright, so an incorrect thing to do is to put the color inside the AES. You can see that when I do that and run that code, I get this odd chart where the points are clearly not purple, they're red, and I've got a little color legend saying, hey, the color red means purple. Right, so it's done everything that we wanted it to do, just not quite in the way we wanted, right? And so what's happened here is that because we've put the color argument inside the AES, inside the mapping, it's assuming that the purple entry there is a grouping variable that has been set to purple for all observations. Right, so once it goes to draw the chart, it's like, okay, I've got a color by the grouping variable called color, okay, and that grouping variable color contains the single group purple, and so I will map each of the entries in that group purple to the same color, and then give a color guide for it. So this is the same no matter what I put in here, right? So I could put complete rubbish, right? And it'll produce the same plot. So it's got nothing to do with actual colors, it's groups. So what it's done is it's assigned a new variable, it's called it color. So there's a new, it's like it's added a new column to the Quakes data frame called color, and every entry in that column now has entry ASDFLKJ ASDFLK. Okay. And so it's coloured each group separately. That's why it's given us a wee colour guide. It's just that there's only one group, right? Which means the colour guide is kind of a bit pointless. Okay, so it's a common mistake if you get a guide that you don't expect, or you get some output that you don't quite expect when you're trying to change the colour. Just make sure you put the colour outside the AES bit. Okay, so to set an aesthetic to the same value for all observations, place the parameter inside the geom, but not inside the AES mapping bit. Right, so we'd want to plot it here. Oh, I managed to mess that up. There we go. Okay, so not inside the AES, but the AES bit has got an open bracket there and a closed bracket there, so that's all finished. And now we've got a separate parameter, color equals purple. Okay, to map an aesthetic to a potentially different value for each observation, place the parameter inside the AES mapping bit, right? It should then come from a column in your data, right? So for example, we could map the color argument to a different column in the data, right? So if we have a look in our data, right, we've also got depth. So we could map the color argument to depth, and then when I run that, it will give a different color for each point in the data set, which is representing the depth variable. So now here I have three variables visualized at the same time. I've got my X, I've got my Y, and I've also got the depth. Okay, so now you can see that this earthquake here, that was kind of a little bit strange in that it was observed very widely, was very deep, right? It has one of the largest depths. So perhaps the reason why a magnitude 5 quake was felt widely was because it was very deep. So the energy from it emanated out more widely as a consequence. And then these two here that were large but only felt at a few stations were shallow, right? And so that might be what is going on with these various outliers. Now, another thing that we notice is that earlier on, we added some alpha, so let's do that again. And when we do so, we can see that by making some of the points transparent, we can see through them, and now we can see that actually where all of the points are sort of stacked up down here, there's actually perhaps more points there than we might have previously thought. We can also see that here. So this point here, there's 2 points exactly on top of each other. And that's seen again here and in various other places, here and so on, where we have a darker point. The only way to get a darker point, all the points should be the same, is if they're layered on top of each other exactly. Okay, so these data have been rounded. A number of stations is a whole number. Magnitude is rounded to 1 decimal place. Right, we've only got 4.0s and 4.1s and so on. So there's potentially multiple observations that are identical. Okay, which would be indistinguishable on a scatter plot unless we can see through the points somehow. Right, so on the original plot where we had no alpha, we can't tell that there's some special points here where there's 2 points on top of each other. They all look the same. Okay, so in this situation, we can't get a good feel for the density of the points. Like we can tell that there's more points down here just because they're essentially forming a line instead of being sort of individual points. But we don't know how many there are, right? We don't know how many are stacked purely on top of each other. Okay, so this is called overplotting. And 2 ways to potentially fix it are 1, transparency via the alpha parameter, and 2, jittering, adding a bit of noise to move each point a bit. Okay, so we've already seen how to do transparency, right? So we can just do it by adding the alpha, right? Let's try 0.3, so there you go. So you can sort of get a sense now for where most earthquakes are. So the vast majority of them, of course, are down here. So all stacked up on top of each other. It also potentially changes our view of the trend, right? Because previously we were saying that it looks reasonably straight, but actually when you sort of, if you took a trend through here, kind of where the average would be, you can see that there's actually a bit of curvature there, right? And we'll look at how to do that next time, how to actually put that trend through. Okay, so that's the importance of overplotting. We can also do it through jittering, so we can do it by just switching our geom point to geom jitter. We won't need the alpha here. And what this does is add a little bit of noise. So each observation, we're altering it, we're changing the data, okay? But we're only changing it enough so that we can distinguish the points a little bit. So by default, this adds random noise to the observations, both X and Y. The amount of noise added is 80% of the resolution of the data. So what's the resolution of the data? Is 80% of the minimum difference between observations, e.g. For x, well, so I guess it's 40% the minimum difference between options, e.g. for x, the values are separated by 0.1, so the amount of jitter is 0.04. Okay, so you can see here that if you look carefully, we still have the vertical banding that we saw. So if we look back at this, this vertical banding due to the rounding, we still have that on this plot here. It's just that within the band, things are being moved up to 0.04 either side. So we still get the banding because the amount of jitter is less than the resolution of the data. Okay. Now there's nothing to stop us making it more than the resolution of the data. So in this case of this chart here, we will have jittered the observation. So if we just run that code a few times, we see that we get, each time we run it, we get a different result because we get different random noise, right? And you'll notice that if you skip through these, you'll notice that the points are actually moving a little bit vertically as well as horizontally. It's a little bit hard to see. You can see it here. So if you look at these 2 points here, right, then you can see that they're moving vertically as well as horizontally. And there's really not much need to jitter the data for the number of stations, because the number of stations have a large number of potential categories. Right, they vary from essentially 0 up to 120 or something. Right, so there's 100 different possibilities for that, whereas there's only about 30 different possibilities for the magnitude. So the magnitude kind of needs to be jittered, but maybe the number of stations doesn't need to be jittered. So we could do that just by Googling. So if you Google for ggplot jitter amount, you'll see that you can do it with the width and height parameters. That then might help you if you go to the help for geom jitter and you sort of look down, you can see that there's width and height. Okay, and if you go and look at them, it says down here, the amount of vertical and horizontal jitter. The jitter is added in both positive and negative directions, so the total spread is twice the value specified here. Okay, and so we might want to go width equals, so 0.04, like I had before, that's the default. In this case, because the resolution is 0.1, and maybe we want height 0, right? So if I do that and run that a few times, then you'll notice that all that's happening here is the points are moving in the X direction, but not in the Y direction. So again, if you look at those same 2 points that we were looking at before, every time I generate a new chart, they've just moved horizontally, not vertically. Okay, and of course I could change the amount of width. So I could say 0.5 if I want, and that would shift the observations a great deal, right? So each observation has moved potentially 0.5 in magnitude, which is quite large, and so you've lost a lot of the detail of the data because you've added too much noise, right? We've obscured some of the features of the data by adding a bunch of noise to it. So we've decreased the signal to noise ratio by adding a bunch of noise. So that's what we're looking at today. Next week we will continue on our ggplot adventure.